Okay, so today we're going to be looking at a few of the harder examples of inductive proofs for divisibility. So we know in induction, for example, we've got our three steps. So we've got proving true for n is 1, and then we've got assuming true for n is k, proving true for n is k plus 1, and then our conclusion. So let's just start from the beginning. So we've got proved by mathematical induction that 8 to the power of 2n plus 1 plus 6 to the power of 2n minus 1 is divisible by 7. So the first step we're going to do is we're going to assume true, assume prove true for n is 1, for n equals 1. So we've got 8 to the power of 2 times 1 plus 1 plus 6 to the power of 2 times 1 minus 1, which is 8 cubed plus 6 to the power of 1. Now 8 cubed is 512 plus 6 is 518. We're hoping that's divisible by 7, which it is. So therefore, true for n equals 1. We know our next step in mathematical induction is to assume true for n equals k. So we're just going to look at our original formula and go, okay, 8 to the power of 2k plus 1 plus 6 to the power of 2k minus 1. And we're going to say, okay, well, for that to be divisible by 7, it has to be equal to 7 times by some positive integer p. And we're going to state that k and p are some positive integers. So k and p belong to the positive integers. Now we're going to prove true for n equals k plus 1. So again, we're proving, assuming, and then proving again. So we've got 8 to the power of 2 times k plus 1 plus 1 plus 6, 2 to the k plus 1 minus 1. So 8 to the power of, that's going to be what? 2k plus 3 plus 6 to the power of 2k plus 1. Okay. So we're then going to see, okay, how on earth can I use my inductive hypothesis here? So our inductive hypothesis has a 2k plus 1 for the power of 8 and a 2k minus 1 for the power of 6. So it's none of the things that we can, it's none of the things that we've got in our original k plus 1. So we're going to have to manipulate this somehow to get 8 to the power of 2k plus 1, for example. So what we're going to do is we might rearrange our inductive hypothesis for 8 to the 2k plus 1. And that's going to equal 7p minus 6 to the power of 2k minus 1. Now we've got a problem because we don't have 8 to the power of 2k plus 1 anywhere, but we could say that this is equal to 8 squared times 8 to the 2k plus 1 plus 6 to the 2k plus 1. So we've just used our index laws to simplify that, and we're just simply going to substitute our inductive step into that. So it's going to be 8 squared is 64 times by 7p minus 6 to the 2k minus 1 plus 6 to the 2k plus 1. We have a go at expanding that, and we might say as well this is by our inductive hypothesis. If we have a go at expanding that, we're going to have 64 times 7, which is 488, minus 64 times by 6 to the 2k minus 1 plus 6 to the 2k plus 1. Now we've got a bit of a problem here because 64 is not divisible by 7. 488 is divisible by 7. So we might think we're a bit stuck. whenever we get to a step like this, we're going to try and get some like terms. So we're thinking, okay, there's a 6 here and a 6 here. So if I subtracted 2 from 2k plus 1, I'm going to get 2k minus 1. So I'm going to say this is 488 minus 64 times 6 to the 2k minus 1 plus 6 squared times 6 to the 2k plus 1, sorry, to the 2k minus 1. So I've taken, using my index laws, I've taken away 2 from 2k plus 1 and I get 2k minus 1. Now I've got some like terms. I've got 488 minus 64 plus 6 squared is 36, which is minus 28 times 6 to the 2k minus 1. And we're sweet because that's all divisible by 7. Take out a factor of 7, we've got 64 minus 3 times 6 to the 2k minus 1, which is purely divisible by 7. Now again, I'm just going to quickly go, okay, therefore true for all n belonging to the positive integers. In an exam, please, you need to write that whole novel that we've learnt about. Going therefore it is proven true for n is 1, and so on. Okay. Number 14. I might do 14 last, actually. Number 14 is interesting. Okay. We might do 14 last. Number 15. Prove by induction that 47 to the power of n plus 53 times 147 to the power of n minus 1 is divisible by 100. So, first of all, we're going to prove true for n equals 1. So we've got 47 to the power of 1 plus 53 times 147. 1 minus 1 is 0, so it's just going to be plus 53. 47 plus 53 is 100. So obviously, which is divisible by 100, so obviously 100 is divisible by 100. The next step, we're going to assume true for n equals k. So we've got 47 to the power of k plus 53 times 147 to the k minus 1. And we're going to say it's equal to 100p, where p is some sort of integer. So we've got p and k are some positive integers. The next step, obviously, is going to be proving true for n is k plus 1. So prove true for n equals k plus 1. So we've got 47 to the power of k plus 1 plus 53 times 147. Now k plus 1 minus 1, the 1's cancel, we just get 147 to the power of k. Now again, we're a bit stuck here because that's not going to be divisible by 100. Again, we're going to have to use our inductive step. So I might rearrange my hypothesis to have 47 to the power of k as the subject. So that would be 100p, taking away 53 times by 147 to the k minus 1. So let's substitute that in. So we can see here we haven't really got a 47 to the power of k, but I could make this 47 times by 47 to the power of k plus 53 times 147 to the power of k. So I could say this is 47 times by my hypothesis, which is 100 minus 53 times 147 to the k minus 1. And we've still got plus 53 times by 147 to the k. Okay, so I've got a bit of a problem here. The problem is that we've got a 147 to the k minus 1, and we've also got a 147 to the power of k. And those aren't like terms. So what we're going to have to do is somehow manipulate one of them to equal the other one, I'm thinking it's going to be most easy if we take off 1 from 147 to the power of k, and we'll see how that happens in a second. So we're going to expand this. We're going to get 47 times 100 minus 53 times 47 is 2,491 plus 53 times, well, if we take out 147, well, this is going to be 147 to the k minus 1. Using our index laws, if we then added them back together, you're just going to get k. K minus 1 plus k is k. So let's figure out what, so we've got 47 times 100 minus, oh, I forgot the 147 to the k minus 1 there. I might rub that out, fix that. Minus 2,491 times 147 to the k minus 1 plus 147 times 53 is 7,791 times by 147 to the k minus 1. Now those are like terms. We add our like terms. We've still got our 47 times 100 minus 2,491 plus 7,791 is 5,300. So times 5,300, 147 to the k minus 1, which is nice because 5,300 is divisible by 100. Take out a factor of 100, we've got 47 plus 53 times 147 to the k minus 1. And we're done, which is purely... Is it EL? I always get this wrong. Therefore true by induction for all n belonging to the positive integers, and we're done. That was interesting. Okay, the last one I'm going to do today is something a bit different. I've never seen an induction like this until I figured it out. And it's using a fact of basic multiplication that we're going to realise in a second. So first of all, obviously, we're going to prove true for n equals 1. So we've got 3 times 1 plus 1 times 7 minus 1, which is 27, which is 28 minus 1, so which is 27, which is divisible by 9. Therefore true for n is 1. We know the next step is going to assume true for n equals k. So we're going to say 3k plus 1 times 7 to the k minus 1 is equal to 9p, where k and p are some positive integers. Now the next step is where it's going to change a tiny bit. We obviously are going to prove true for n is k plus 1. That's always the step for induction. Or it's not always k plus 1, sometimes it's k plus 2, but we haven't seen like ones like that at the moment. So prove true for n is k plus 1. Let's have a look at what it's going to be. We've got 3k plus 1 times 7 to the k plus 1 minus 1. If we simplify that, we're going to have 3k plus 4 times 7 to the k plus 1 minus 1. Now, I'm not going to do the incorrect strategy any further than this. If you have a go at doing the strategy we learned in class, if you rearrange your inductive hypothesis for, say, 3k plus 1 times 7 to the k, or you might rearrange it for something, maybe you rearrange it for 1 or whatever you'd like, you're not going to get the answer and it's not going to work. So if you are faced with a question like this in an exam and your substitution is not working, there is another strategy that also works. So if we have a look at, say, the number 18, if we take away 9, we get 9. If we have 27, take away 9, we get 18. If we have 36, take away 9, we get 27. So what I'm trying to get at here is if we have any multiple of 9 and we take away 9, we're going to get another multiple of 9, and that's going to work for any number. So we might say f of k plus 1 minus f of k is also divisible by 9. So what that implies is that n equals k plus 1, our expression for that, minus our expression for n is k, is going to be divisible by 9. So our expression was 3k plus 4 times 7 to the k plus 1. And we're going to take away our expression for n equals k, which is 3k plus 1 times 7 to the k minus 1. And that's using our hypothesis. So again, if you have a multiple of 9 and you take away 9, you're going to get another multiple of 9. That's what we've written here. The next multiple of 9k plus 1 minus the one before it, or minus 9, is still going to be a multiple of 9. So if we have a go at expanding that, we're going to have 7 times by 7 to the k plus 1 times 3 to the k plus 4 times 7 to the k plus 1 minus 1 minus 7k times 3 to the k minus 7 to the power of k minus 1. Now we're going to try and collect like terms. The best strategy is to get rid of our k plus 1s by taking out that 7 using our index laws. So if we take out a 7 from k plus 1, we're going to have it 7 times 7 to the k times 3 to the k times 3k plus 7 times by 4 times by 7 to the k minus 1 minus 7k times 3 to the... Where did 3 to the k come from? Sorry, that should be 3k minus 7 to the k minus 1. Okay, we can have a go at simplifying that again. 7 times 3 is 21, so 21 times 7 to the k. Then we've got plus 7 times 4 is 28 times 7 to the k. Now I've missed something again, that's going to be 21k. 7 times 3k is 21k, plus 28 times 7 to the k. We've still got a minus 1, minus 3k times 7 to the k, that hasn't changed, minus 7 to the k minus 1. And that I'm not going too well today. 2 minuses would make this a plus on the end. So if we have a look at this minus would make that a plus there. Okay. If we have a go at collecting our like terms, these are our like terms here and here. Now 21 minus 3 is 18 times 18k times 7 to the k. And then here we've got 28 minus 1, which is 27. So plus 27 times 7 to the k, and then minus 1 plus 1 is 0. Hopefully we can see that this is now divisible by 9. So we can take out 9. This is going to be 2k times 7 to the k plus 3 times 7 to the k, which is purely divisible by 9. Therefore true by induction for all n belonging to the positive integers. Beautiful. Okay, hope that makes sense, everyone.